Thank you very much for the giving me opportunity to talk. My name is Richard Harvik. So I separate myself from the rest of the team who have done the real work. Now that I'm trying to take myself out, I'm standing on the shoulders of giants. So they've done all of the work. But all the crap I'm going to say today are my own opinion, not Amazon's opinion. Okay, so and I'm trying not to look at red. So when I say something bad, you won't give me any eye. So I'm going to skip a few slides. We are here. We all agree graphs are awesome, but I'm here because I love them. It's fun. Okay. So I don't have a slide about me, but I put this slide to explain who am I. So I am one of the young ones who got his PhD in last millennium on sparse computations. Basically, my PhD was about how do you partition the work, sparse work, so that you can actually reduce the communication. That's all it was about. So I'm coming from really hardcore HPC side, and I've done quite a bit of graph analytics, and I've published lots of, some junk graph algorithms paper. We tweeze out the kernel we want to optimize, and we pick the hell out of it and just get the fastest algorithm out there. I took the blame like many others who have done it. But the world, in my view, the graph world is actually three different worlds, right? One is enterprise graph world, where so that Prebbles, giraffes, and they don't really care about performance; they care about productivity, which is great. It's some, but they can be orders of magnitude slower than anything we can do even sequentially, right? And there's the graph database work, which I've been foreign to until I joined Neptune. So I'm not a database guy, so my apologies if I will insult some of you here. So what are we trying to do? We are trying to get in the middle, right? So we all know that one size doesn't fit all, okay? We cannot do best of everything in one single product. But what is the boundary, right? How close we can get, right? So my goal is, can we develop a system that at the end, the performance is a small constant factor of the best we can do, right? So I play sometimes theory guy, so 1,000 is a constant, right? So I don't want to be 1,000 times slower. I just want to be, okay, 2 to 4 times slower than HPC, but at the same time provide transactions, crash recovery, and everything, right? So can we do that? That's what we're going after, okay? And as I said, subsystems don't care about productivity, and how do you measure productivity is another thing, and I'll come to that in a bit, okay? Again, I'm going to skip this slide because you guys are the expert of this. I just learned these last year. So there are two worlds, and Neptune, we used to provide those two worlds separately, and I was bold enough to put that we want to do one graph to rule all, right? Or I explain why we need to do this, why it's needed. So my talk is about, 15 minutes is not enough to describe what we have been building, but I will try to give you a glimpse of what are we trying to do and how we are going to achieve, and hopefully convince you without giving real numbers. Okay, I'm sorry, I don't really have. I have some numbers, but not final numbers here. Okay, so really, we want to serve both of the worlds, RDF and LPG. So we want to provide 1G graph. So rubber has to meet the road. So at some point, I need to represent all of this in computer system in some way or the other. So how I'm going to represent them, how do I store them, etc. Right? And anyone who has done HPC or anyone who's trying to do anything fast knows that it all boils down to data locality at some point, right? So you don't want to ship data, even from memory to CPU, right? You want to keep it close, keep in your L1 cache, L2 cache. You want to keep in the core. You want to keep in the distributed memory. Sorry, I've published many distributed memory papers, 2005 for Nobel Prize nominee paper on BFS. Yes, there was no need to publish that paper, but I was an academician at the time. we need to publish, and that's that. Okay. So how do we see the world, 1G world? So in 1G worlds, the storage we have is basically have three types of general relations. One is dictionaries. Those are your URIs, literals, that unique identifiers you want to call your vertices. Okay. So again, in HPC world, the vertices are from 0 to n minus 1. So how convenient. The life is not like that, right? So then we have the graph structure itself. How do we actually connect those things? So coming from RDF world, maybe it's subject object. So basically those are vertices, how they are connected. Then we have the graph data, the values. Those values could be properties of vertices, properties of edges. And we like to make it complicated, and at the end, I'm still academician, edge properties, edges properties, they can become vertices and edges, and all can get really haywire. Okay? So we'll handle all of them. We'll see how fast we'll be in all of them, but we'll handle all of them. So, okay, I said we need to keep the data local. So we need to somehow partition the data. So even if you're running on a single server, you want to make sure that your data is partitioned somehow, so that you're not jumping between two caches of just NUMA out of NUMA, etc. Right? So we are sharding, we are partitioning. It's a chicken and egg problem, and I'll come to that. So basically, let me say at this point, just the 1G, the dictionaries and the properties, the values will partition in 1D. The graph itself will partition in 2D. Okay. Graph is not static. Well, for all of you, you knew that. And obviously, we can come up crazy data structures to make it more efficient, etc. But again, we are trying to do everything. We want to be asset compliant, transactions, crash recovery. Right? I cannot always keep just memory pointers in my data structure. So when it crashes, it's gone. So just need to take care of all of these. Of course, deletion, etc. I need to do that. And the graph is coming to me, right? So it's not given to me. In my PhD, I assume it was given to me. Then I figured out how to partition them. So I know how to partition them if you give it to me. But if it's streaming, no one in this room or in this world can say that I'll know good algorithm how to partition. Okay. So what you need to do is you need to do best of both. So what we are doing is what one of the reasonable solutions, in my opinion, is trying to achieve load balance. Okay, we are trying to do. We will still do the data locality, but not in the sense that these vertex and these vertex are related, so let's put them together. But we're gonna say these bunch of vertices and these bunch of vertices, their edge goes together, and I'm gonna process them as a bulk, right? So this will probably tie very well to TileDB talk later. I haven't seen the talk, but I assume it will be very similar in some sense. Okay, so but of course, at some point, if you realize this is my graph, or this is 90% of my graph, right? After that, the change will be minimal. We can repartition everything. We can make it more data local, etc. Okay, so sharding options. People have done zillion different things, and the choices are obvious. You distribute 1D, the one node, and all of its edges goes to somewhere. You can do edge partitioning. You can do random partitioning, or you can use smart models I developed 25 years ago to give single edge to a processor, or you can do block partitioning. Again, I think still no one else other than me developed an algorithm to do smart coarse 2D partitioning. Okay, so we are doing 2D partitioning. This is not an eye exam. I'm not expecting you to read anything on these slides. I will just highlight that like many academicians, I picked 5-6 algorithms I thought important, and you will see the same corpus. You will see LBC graph analytics algorithms, but I also have triangle count in it, so I have a couple other kernels there. So I compare one of the systems that my PhD students developed, we call PGAP, parallel graph algorithms by blocks, to against the state of the art in the HPC world, right? Those are the fastest ones, Gandra, Galois, LA graph, LiGraph, right? So, and we tested that against different kinds of graph, okay? So one thing, and these are all normalized against the Scott Beamer's GAPPS results. So anything less than one, the algorithm was doing the implementation of in that platform for that algorithm for that data set was doing better. So one obvious thing, there's no clear winner, right? So there's no way. So anything red doing bad, anything green is doing better. GPU systems will fail some of the large graph because they won't fit to GPU. But with the PGAP or basically to the partitioning idea, you can actually move things in block to GPU easily, right? And that's what we are doing. That's why we were able to handle that, even just using GPU, or we can use heterogeneous systems, right? So that's all about. So that's why we are using a very similar to the partitioning idea. Okay. So how about computational models? So what kind of computational model we are using? Or obviously, think like a vertex is easy to program, but we are exposing a partitioning constraint. So you really need to think about a block. You need to think about tile, a subgraph, but with well-defined constraints, which really allows us to limit those aggregations or accumulations in a certain way. We can optimize them much better, right? So, I mean, these are not new, right? So we, in sparse matrix community, we have been doing those things. It's just the same things, just doing it. So, externally today, that's our plan, and what else we will do, you can ask Brad, okay? So I'm not going to talk about OpenCyber when we're going to have a graph API. So I didn't put this slide, this bullet this morning, or it was there yesterday. It was there a year ago. So GraphLabs is a really low-hanging fruit for us because we are really doing tiled matrix computation, right? So we can easily provide an implementation of GraphLabs, which eventually will have a distributed version of it as well. Okay. Okay. The scalability. Okay. Yes, we don't need 1,000 machines, but I do have customers that would require 4 to 8 machines, and there might be some can go up to 64. I don't think it's going to give anything beyond that, right? That would be unrealistic. The structure of the graph, I agree, it's going to fit in single node. Okay. The problem is the graph database is not always totally external. They try to stick with some identifiers that are long. Those identifiers keeping lots of memory for me, right? So that's the reason we would need a few more nodes, not the structure itself. Okay. So read scaling is obviously easy. Handling transaction is difficult. So what are we building? We are building basically in-memory first, right? Transactional. So we will be graph natural database in-memory first. Transactional asset recovery. So what does it mean providing graph analysis on the transactional system? We can have other academic discussions about this, right? What does this mean if I'm running PageRank, a new edge edit, delete to build my PageRank converge, etc. We allow all of those, and we can limit that however we want. So basically, we will be running the algorithms if you tell us on top of your transaction data, and we will be basically hiding some of the dynamic creation of reviews and for multi-iteration algorithms, etc. Right? Whenever it's needed, we have to do those always. There was some mention about sharding killing the performance. Yes, partition will kill your performance if you have a weird graph like EuroPOSIAN, which is basically a roller. It's a pattern graph with average degree 2, right? If you do the 2D sharding of that, running BFS, you're not going to take any advantage of parallelism because, well, average degree 2, there's not much work. And you really need to look at multiple partitions to find, oh, I only had two edges which were in this two partition. But for other algorithms we've been developing, PageRank, closing centrality, or anything, right, it still helps. So again, we cannot be the best everywhere, but how it works will be is the key, right? So, and we want to be as close to as optimum in many cases. Okay, so at the end of the day, the question is, can we implement once and run everywhere, right? That's what we are going after, right? So we are running on multi-core host today, and multi-host is an acceleration is obvious extensions, right? So we have been developing Porcelain label data flow. You can think of a task execution system which allows you, because of we are doing tiles, right? We can do all of those pipelining things and moving things around, while computing, moving things in and out, all of those things, right? So can we really do that? Well, we are doing it, right? So with a native storage system, with advanced kernels that are smart enough, and with state of the transactional system, we have MVCC, etc. All of these. So again, many people in this group actually developed it. It's not just me. So yeah, I think at the end of the day, I think these are all doable. Again, if you want to tease out, can you do this fast? Maybe not that fast, but I can do everything else. So that's what we are going after, right? So can we develop a system that can serve both RDF community, open cipher community, everyone, PG community, but still also provide really high throughput, high performance graph analytics. I'll stop here. Thank you.
Questions? Hi, thank you for this interesting talk. Actually, with dealing with GPU and the hierarchical memory in solving graph problems, you mentioned that using block method, and you can try to load one block into GPU memory, so far, so good. But however, have you considered some extreme cases, for example, when considering the LDBC data, person living in a country, and for countries like India, there are billions of people. And however, partition, no matter what strategy you use, and there might kind of block them, it's not possible to get rid into this GPU device. So have you considered such extreme cases?
So again, one can always create a really pathological case. Right? So we are doing smart sharding. We are limiting our partitions, right? So and we are taking advantage of really some random number hashing, etc. All of these to do the distributed cases. This is not gonna solve your give me distance to queries in GPU forever, right? So that will be a certain queries that's gonna still always live in CPU, right? So GPU will be good for when you're doing PageRank, when you're doing more computationally extensive analytics. There's no limit that you cannot do some of these things in GPU as well. And we don't have to always ship the full block in some cases. So we are doing MVCC, we can actually move the delta as well. There are other techniques. But can you come up with a data distribution that will, the scale? Yes, you can. Any more questions? Leon? Here's my
because that is a database, so obviously you have to maintain another copy for this HPC graph analytics, right? So how is the data synced? Is it real time or on demand?
There is a single copy, right? So for redundancy and everything else, we will make copies. But when we are running graph algorithms, we are actually running on the same data set.
I see.
On top of transaction, I'm reading from the transactional memory system, right? So.
But the computation resource will it share the database, or
there will be some ephemeral data for the algorithm to work, right? So if you're computing PageRank, if you're not gonna store them in the database, right? while you're computing, we are of course not storing them inside of the transaction. Those are ephemeral data while you're running the algorithm. But at the end, of course, you can stream back them to the properties. You can write them back to the source.
I mean, maybe the graph analytical algorithm may take lots of memory, and so it will co-locate with like database instances. I mean, it will like eat up all the.
How do we partition the memory for the actual storage and the computation, right? So, using a simple ratio seems to work fine for us for all of the algorithms we have developed so far. But again, since we are developing the algorithm, we know the time complexity, we know the storage complexity, we can adjust all of those.
Okay.
All right, thank you. Next is David from Tavares, and he's one of the local forces.
Local? Wait a minute, I just moved to Minnesota. Yeah. Tavares is. I chose to live in Minnesota? Oh my goodness. And here I was shooting for 10 minutes, and we're off into Minnesota. All right. Okay, just a brief outline. I'm going to talk about what our app is, and maybe talk about why it might be somewhat different from what most of us are thinking about these last couple of days. I'm going to talk about the features of LWC that we find really useful and how we use it as an example, and then just give some thoughts maybe for some enhancements to Graph Linux. So just what our architecture is. So we have a compute server. So what was it that was saying? A single server is big enough. So I've run this on a 24 terabyte server with say 572 cores. They're not common, but they are available. A 32 gig or 32 terabyte system is going to come available to me in a couple of months. I'm looking forward to that. But I can also run this on a laptop. I can run this on an EC2 instance with 1 gigabyte and 1 core. So, in fact, I don't even need to recompile. I just move the executable. It's kind of fun. Our user interface is external. It's a Python script, effectively. So, our intended user base is a data scientist. And unlike graph algorithms are slow, cipher queries are fast, they're transactional. We count them in number of transactions per second. I focus on things that are cipher, they're subgraph isomorphism, but they may take like 24 hours to run. And I want to try to run them in 1 hour instead. So that's kind of the goal here. So we are not a database, although we are transactional. So we can do multi-user. We do atomicity, consistency, isolation. We just don't do durability. We do have some whole graph algorithms. What we're hearing from our customers is, I don't care about BFS. I want to do my own derivation and manipulation of something like a BFS. And so the fact that we have BFS is not necessarily all that helpful. We're trying to make it more general, more flexible. Okay, the features that we find really useful are the data sets. The SNB data set in particular is the most real-world synthetic data set I've seen. I've done a lot of work in cybersecurity, and cyber people know that if it's a synthetic data set, it's completely useless. So they don't even try. So it's multi-typed and reasonably large. When I say reasonably large, it doesn't fill up the 24 terabyte server. But actually, we do run pretty well on modest size systems. So 32 gigs of memory, 8 cores. It's a pretty decent engine anyway, even at that size. And the BI queries are interesting. A lot of them are seeded. Again, it's that whole look up something. I want to do multiple transactions per second versus I want to do something really hard. Find a very rare pattern, and It's going to take a lot of search. So what we've done is we used 4 different data set sizes. This is a study we did a couple of years ago. I've added a bullet here. Let's see, Alistair, can you identify which bullet is new as of yesterday? Yeah, some statistics about this. So the number of edges on the scale factor 1000 is only 17 billion edges. I have done 300 billion edges using this product on that 24 terabytes. So we don't think of 17 billion as necessarily the top end of our sizes. We're looking for queries that were going to take longer than a simple lookup. And so we developed some of our own queries. So this is clearly not sanctioned by LWC. And on that website, thanks to Gabor, I put a statement on there saying this is not part of LWC, not sanctioned. Yeah, but these are the 4 queries, and I'm not going to show the graph pattern, and I'm not going to show the cipher. I am going to talk about the difference. We have HPE, this really pretty small system, 256 gigs of RAM, 32 cores. HPE Superdome Flex 280 had 6 terabytes of RAM, which is really pretty small these days in terms of big enterprise servers, and 224 cores. So what we did is we ran with just 1 socket on that Flex 280 and then all 8 sockets. And this is what we found, and you can see the performance of, and we actually didn't count just the number of edges in the graph, we actually counted the number of edges we traversed in the search. And you can kind of see the number of actual traversed edges correlates very closely with the running time. But in this way, we can show this to a customer and say, you know, you're thinking about getting a Flex or just a DL380 or DL385, you choose, right?
These are runtime, smaller is better.
These are run times, so their number of seconds, yes, smaller is better. Yeah. Yeah, time in seconds down here, and traversed edges in units is 1 million traversed edges. So can I be so bold as to suggest maybe ditch the .java? Sorry.
Yes.
You know.
Please.
I inherited it. Yes.
Yeah, I mean, I tried Graphalytics, and I spent more time just dealing with Java than I did with anything else.
Well, that sucked.
And I gave up. Let's see. I've already made this statement. Nobody really wants that BFS. They want to do their own variant. And the output. Why do we insist on having the output be the number of nodes? What customers really want is just the nodes that are reachable. So I did actually run BFS, and I found that I spent half of our time just making sure that we wrote a bunch of plus infinities for the nodes that were not reached. Kind of seems missing the point. Some other ideas, since graphs are not static, how about something along the lines of, let's read in 90% of the graph of the edges, run BFS, read the next 5%. Oh, and we're capturing the time of making the adjustments to the graph itself as well, as part of the benchmark. Because I think you'll find that real-world graphs change over time. They're rolling graphs. And so that's just a thought. And really, see how am I doing? Yeah, I'm coming close to my 10-minute mark. We want to talk about Minnesota?
No, that's fine.
Questions?
Okay, I guess Longwin had a talk yesterday about extending Graphalytics. So, do you have any comments regarding things like the dynamic variant of Graphalytics for future benchmarks?
Yeah, I agree. Most of the things, especially Java implementation, because we've confronted a lot of dependency issues. Plugging the LDPC graph analytics benchmark system. But about the dynamic processing, not sure because it will add complexity to a lot of algorithms. If we just target the FS, it's fine. But I think by direction, so kind of very, very clustering coefficients, they would be just nightmare if we consider such kind of thing.
Yeah, I agree. Doing this, you have to start the timer after the 90% edges, and then you have to run BFS, capture the output of that, ingest 5%, run BFS, capture another BFS output, and then capture a third BFS. So you have to validate 3 times. It gets a lot more complex. I agree.
So that will make the like incremental systems like more compelling in this analytics.
Yep.
Yep.
Cool.
That's 90 minutes.
Yeah, definitely. I will put into consideration while visiting. Yeah, we didn't consider this point. Thank you.